Okay, good morning, everyone. I hope you managed to get some respite on respite day last week. We haven't seen each other for a week. So hopefully you're ready to tackle evolutionary robotics again. As always, just a couple of housekeeping notes. Hopefully last night you managed to submit your first weekly deliverable for the final project. Again, the link for that contains all the information about the final project is here. You're starting in on your second weekly deliverable today, which will be due, as always, next Monday night. Just as a reminder, if you're following the easy track, you're submitting 3 different mini projects 1 week after the other, which gives you a chance for if something doesn't go well with one of the mini projects, you can start in fresh the following week. For those working on the hard track, you've chosen one of the hard options, or you've been in contact with myself or the TA to formulate and verify a final project idea of your own. Okay, I hope you managed to take some time last week to refamiliarize yourself with your code base. Again, you have a considerable amount of code now, and as you probably are very well aware, in order to make progress or to make small or significant changes to your code base, you need to know where everything is. I'm not going to review that today, but just to remember, most important thing to do is to be very strategic in placing exit statements either in the search.py code hierarchy or the simulate.py code hierarchy. So you can, in essence, cut them in half, have one part do some part of your functionality, and then be able to manually run a simulation to make sure files are being read in correctly, the simulation is working as you expect it to work, and that it's writing out whatever fitness file or fitness files, plural, you expect to get back. Okay. Robbie was mentioning this morning about Pyrosim. There's an older version of Pyrosim that was used in previous years, previous versions of this course. Pyrosim used to sit on top of an older physics engine known as Open Dynamics Engine, or ODE. We don't use ODE anymore because it's not cross-platform. So this year I've taken Pyrosim, unhooked it from ODE, and attached it to PyBullet, which is the physics engine that we're working with this year. I have not yet exposed all the functionality in Pyrosim, in the new version of Pyrosim that used to be in the old version of Pyrosim. For those of you feeling ambitious, you can reach into your own version of Pyrosim and expose different parts of Pyrosim, different features of PyBullet that are currently hidden from you. For example, up until last week, you could only create cubes, but PyBullet allows you to create spheres and cylinders. I put a little section in the Reddit page about how to modify Pyrosim so that you can expose spheres and make use of them in your simulation. You can do the same thing for cylinders and for some of the other aspects of physical simulation. A good place to start if you're thinking about doing that is to Google the PyBullet Quick Start Guide. The documentation for PyBullet is not very good, but what documentation exists, almost all of it is in the Quick Start Guide there. So you can sort of browse through all the various features in the PyBullet physics engine, and you can, by making some changes to Pyrosim, make them available for your code base. If you get stuck, come and see Amanda or I, and we can give you a hand with that. I see there's a hand up. If somebody has a question, go ahead and unmute yourself and ask it.
Yeah, I was wondering how you felt about bringing in other libraries, like for visualization other than Pyrosim or PyBullet.
Absolutely, yeah, that's a great question, Missy. Absolutely. So for those of you that want to use other Python libraries for anything, visualization, analysis, it's all good at this point. The final project is your opportunity to really flex your muscles and pursue your own ideas. That's perfectly fine. The one caveat here is that we want you to keep using the physics engine. So rather than swapping the physics engine out for something else, like there's a Python game library, 2D graphics, We want to make sure that your robot is embedded in a physics-based world. So you can add any libraries you want, but we'd like you to carry on working with Pyrosim. Good question. There was a comment this morning that if you add spheres to your world, that your robot may not collide with the sphere. I'm not sure if that's true, but I wouldn't be surprised. I wouldn't be surprised if it is true. We talked at the beginning of the course when we were talking about physics engines about collision detection and resolution. In order for a physics engine to detect and resolve collisions between different object types, the physics engine needs to support collisions between cube and cube, cube and sphere, 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 cylinder, cylinder, sphere, cylinder, cube, and so on. There's a lot of pairwise specific cases that need to be handled. The default for some of those cases is to not detect and resolve the collision. For those of you that are doing the Project Runway project or the Full Steam Ahead, where the robot comes into contact with cubes in its environment, you'll know that by default, PyBullet respects those collisions. It does not allow the robot to pass through platforms and cubes and so on. The default for cube and sphere collision, the default may be to have that turned off. If that's true, and I haven't had a chance to check that yet, that means that if you put a sphere in your world environment and the robot comes into contact with the sphere, it will simply just pass through the sphere. If that's true, and again, I'll check that later today, there is a way to flick a switch and turn that back on. Okay. Any other questions about physics engines, details about the final project? All good? Okay. All right. So back to the matter at hand, which is looking at open problems in the field of evolutionary robotics. We're making our way through arguably the biggest open question in the field, which is evolving things in simulation and then reliably transferring them to reality. We looked at adding noise to the simulator. We looked at 3D printing as many evolved simulated robots as possible in the hope that at least a few of them cross the reality gap. And we started in last time by talking about my humble contribution to this problem, which has become known as the Resilient Machines Project. We'll return to lecture 17 and finish it in a moment, but just to remind you, big picture in the Resilient Machines Project is we have two evolutionary algorithms. One is evolving controllers for the robot in simulation, as always. The second evolutionary algorithm is evolving simulations themselves. And the fitness function of each simulation is how well it reflects reality. So the idea in the Resilient Machines Project is to evolve a simulation that becomes closer and closer and closer to reality. And that's a way to close the reality gap. Okay, we'll finish up lecture 17 today and then dive into transferability. Okay, so I started by walking you through a typical experiment in the Resilient Machines Project last time. We have our 9-segment quadruped. We tell the quadruped that it's made up of 9 parts, but we do not tell the robot how those parts are put together. So the robot is going to have to try and evolve a simulation in which all of these parts are arranged correctly. Remember that this robot does not have a camera. It can't see itself. It only has 2 sensors, 2 vestibular sensors. The first vestibular sensor tells the robot how much the main body is tilted left and right. The second vestibular sensor tells the robot how much its main body is tilted forward and back. The way to build up an intuition for this project, as I mentioned last time, is imagine yourself in a black box, no windows in this box, and you have 8 levers in front of you, which correspond to the robot's 8 motors. When you pull on some of those levers, meaning you rotate some of those motors downward, you will feel the box in which you are tilting left and right and forward and back. And you need to then take that action, sensory reaction, or sensor motor data. You need to take that and infer where all the motors or where all the parts are arranged relative to the main body, relative to this windowless box. Okay, so in this case, the easiest thing to do at the beginning when you don't know much is simply to pull the levers at random, which is what the robot does. In this case, it rotates motors 1 and 5 down, and the other 6 motors it rotates up. And as we can see, the robot's main body tilts to the right. The robot is then going to start up. The evolutionary algorithm that is going to evolve populations of simulations, where each simulation contains a different arrangement of the 9 parts. So you're watching the early stages of the evolutionary process here, where it's trying out each different arrangement. And I apologize for my camera work here. The physical robot rotates to the right, and the camera from the robot's point of view is actually pointing this way. So you'll notice that in this video, the green box tilts away from us towards the end of this video. The robot is tilting away. If the camera is looking from the right-hand side here, if you imagine looking at this view from the right-hand side, the green box is actually tilting to the right. Again, my apologies for not recording this correctly. What this means is that at the end of this short video, at the end of this short burst of evolution, the robot has found actually multiple descriptions of itself that match the sensor motor data. The physical robot says to itself, when I rotated motors 1 and 5 down, I tilted to the right. And assuming I'm put together like this, when I rotate motors 1 and 5, wherever they are in here, I also tilt to the right. The robot's confused at this point, however, because there are multiple descriptions. There are multiple individuals or multiple simulations in the population of simulations that all tilt to the right. The robot knows enough to know that it can't be put together in multiple different ways. Either one of these simulations is correct, or none of these simulations is correct. There is yet some other way the robot is put together that explains this data. And we know, from our distal or distant perspective, we know there is a different way the robot is put together. It's this way, and this is the correct way. But the robot doesn't know that yet. If you were the robot, what would you do next? You've performed an action with your physical body. You've rested for a while and run this evolutionary algorithm where you're thinking about how you're put together. And you've come up with multiple explanations of how you're put together that all explain the physical sensor data. What do you do next? If you have an idea, go ahead and type it into chat. Do something to break those possible body types. That's exactly right, Hannah. So the robot is going to try and perform a second action to disprove what it currently knows. So Hannah says break, and I'm going to say disprove. We're going to think, as we move forward, we're going to think about these simulations as hypotheses. In essence, this is the robot saying to itself, if I were put together in this way, and I rotate motors 1 and 5 down, this is what I expect should have happened. It's got some hypotheses, it's got multiple hypotheses for what's going on. So the next action it's going to perform is not random. The first action it performed was random because it didn't know anything at this point. But now it knows something. The next action it's going to perform is non-random. And that action is going to be chosen, as Hannah says, to try and disprove these current simulations. Okay, before we move on, however, I just want to talk a little bit about the fitness function here. What is the fitness function of each of these very short simulations you saw? The fitness function is to minimize the distance between the physical vestibular data and the virtual vestibular data generated by a given simulation. So here's a different action. This one causes the robot to stand up on its front and back toes, and the main body actually stays level, so there's no tilting here. Here's one hypothesis or one simulation. If this simulation performs the same action as the physical robot does, it tilts to the right. And the difference between the physical vestibular data and the simulated vestibular data, there is a non-zero error. So that's bad. Here's a different simulation, which as we can see is actually a correct description of the robot's body. This one also produces simulated vestibular data, which is that the simulated main body does not tilt, and the error between the physical vestibular data over here and the simulated vestibular data over here is 0. So we're going to run an evolutionary algorithm that doesn't try and maximize the displacement of the robot. It tries to minimize the difference between physical sensation and virtual sensation. Okay. So let's carry on with this experiment. This robot is now going to perform a second action. And as I mentioned, this action is not random. It was chosen to try and break or disprove the hypotheses. I'm going to set aside a discussion of how it actually does that for the moment. We're not going to talk about how it chooses this second action. Just trust me for a moment. It chooses a second action. And in this particular experiment, it chose this second action, which in this case causes the robot to tilt a little bit to the left. So now the robot has 2 pieces of sensor motor data. In the first case, motor 1 and 5 down, tilt to the right. In this case, I'm not sure which one it is here, it doesn't really matter. Motor 2 down and tilt 10 degrees to the left. It's got 2 pieces of data. So now the robot is going to rest on the ground again, and it's going to start up the evolutionary algorithm, and it's going to sift through, or it's going to continue evolving simulations. But each simulation is going to be played twice. The first time, the first simulation, motors 1 and 5 are going to tilt down, and the robot is going to record the resulting simulated vestibular data. Same simulation is going to be played a second time, but this time motor 2 is going to be rotated down, the second action. And again, the resulting simulated vestibular sensor data is going to be measured. And the fitness of every simulation now is the distance between the 2 sets of physical sensor data and the 2 sets of virtual simulated data. So it's going to get harder for a simulation to be correct because that simulation is going to have to explain or reproduce 2 experiences that the physical robot has already had. Make sense? Okay. Okay, so the robot's performed 1 action, 1 round of evolution, a second action, and this video which I'm playing is actually not a video produced after the second action, but this is actually after the 8th action. So the robot, the starfish here, the evil starfish, alternates between performing an action and getting some experience, doing some evolution to try and search for an explanation of itself, search for a simulation that reproduces physical data, act, simulate, act, simulate, act, simulate, act, simulate, and so on. I picked this particular video from the 8th round. This is just after the robot performed the 8th action, because during this moment in time, the robot had its eureka moment. You'll see that at the beginning, it doesn't have a good explanation of self, but partway through this evolutionary process, it discovers how it's put together. If you watch carefully, for a short period of time, it'll get 3 of the 4 legs correct. So the robot now knows where 3 of the 4 legs is. This particular simulation has evolved and explains almost all of the 8 experiences the robot has had so far. This particular simulation produces some offspring with mutations and eventually produces this simulation, which is now very close to the robot's actual physical structure. It's not perfect. You'll notice some of the legs are still bent, but this simulation explains almost all of the robot's 8 experiences. So far, so good. Any questions? Guess I can maximize this here. Okay, so back and forth, back and forth. This is still the same experiment. This is the robot's 16th and final action. Tilts a little bit forward. And this is the 16th attempt at evolving a description of itself. And this is what's going on inside the robot. All of the simulations have converged on an almost perfect explanation of its own body. But again, the explanation isn't perfect. The legs are bent a little bit. So the robot has been able to evolve a simulation to describe itself. Now that it has a description of, now that it's evolved a simulation, we turn off that first evolutionary algorithm and turn on the second evolutionary algorithm, which is going to be much more familiar to you. This is where we evolve populations of controllers to get the robot to do something. In this case, we're evolving controllers to get the robot to move from left to right. And this is the best or most fit controller, neural network controller that the robot came up with. We take that evolved controller that was evolved on an evolved simulator, transfer it onto the physical machine, and this is what we get. Okay, so that's stage one of the Resilient Machines project, where the robot is able to not only evolve the ability to walk, but it's able to cross the reality gap because it's evolving accurate simulators. Last time I told you that this project was funded by NASA. NASA was interested in developing what they call methods of last resort. If something goes really wrong with the rover and it's very difficult for mission control to diagnose from Earth what the problem is, at that point, when the mission is in danger of complete failure, NASA may consider ceding control to the robot, allowing the rover or the probe or whatever it is to become more autonomous and to try and diagnose the problem itself and come up with a recovery strategy. So to demonstrate that, we're going to basically just keep this experiment going. At this point in time, at the end of phase one, the robot has an accurate simulator of itself, and it has a controller that fulfills the mission. And the mission here is just move from the left side of the table to the right side of the table. We simulated a nearly catastrophic failure, which is we sent a grad student in with a screwdriver and he mechanically unscrewed the right lower leg from the robot. So that now when the robot performs, some of these exploratory actions, it gets a different result. You'll notice in this case, it just happens to be trying to rotate its right leg downward. You'll notice that the motor is still attached here, so the robot is still sending commands. You can still pull on the lever inside the windowless box, but you get a different result in this case. So from the robot's perspective, it knows somehow that last time when it rotated the two motors in motor, I don't know what motor this is, 3 and 7. When it rotated motors 3 and 7 down, before it would tilt about 40 degrees to the left. Now it only tilts 10 degrees to the left. So during the mission, from time to time, the robot stops the mission and performs some of these exploratory actions again. And if it detects that something has changed, and by something changed means I did this action before, but now I'm getting a different sensory result or a different sensory repercussion, that's the signal. The robot knows that that means something has changed. So the robot stops the mission, tells mission control, hold on everybody, something's wrong. Let me see if I can figure out what the problem is. The robot now has 17 experiences. Remember, it was doing 16 before. It now has the 17th experience. So it starts up, it unpauses and starts up the first evolutionary algorithm, which is evolving simulations. One detail I forgot to mention before is that I told you that the robot is going to try and evolve an arrangement, a way of attaching these 9 pieces together. We also allowed the evolutionary algorithm to change the size of these pieces. That seems like kind of an odd thing to do because parts of the robot are unlikely to suddenly increase or decrease in size over the robot's lifetime. But actually allowing these pieces to change in size and volume and mass, change in size and therefore volume and therefore mass, allows the evolutionary algorithm to actually come up with simulations that describe a lot of the things that actually can go wrong to a physical machine. For example, if it loses a leg, there's less mass on this side. If the robot is walking and it sticks its leg into some sticky mud and pulls it out, that leg is now bigger and heavier than it was before. Rather than simulating mechanical damage or simulating mud or simulating sand or simulating whatever else, the 1,000,001 other things that can go wrong, we allowed evolution to modify the sizes of the robot's body parts, and that turns out to be allows the evolutionary algorithm to approximate or explain a lot of the things that have actually gone wrong. You'll see that in this video. The robot has just performed the 17th action. Each simulation is evaluated 17 times. I'm only showing you 1 out of those 17 for each simulation. These are the simulations that the robot evolves. I'll play it again a couple times. You'll notice at one point the robot actually hits on the right explanation. This evolutionary algorithm has a little bit more noise in it than the evolutionary algorithm you're working with. So the robot actually loses this good explanation for a little while. It hits on this simulation, which is that its leg is actually smaller than it is in reality, which obviously doesn't make a whole lot of sense, but is actually kind of close. And it eventually it returns at the end to the correct description of self, which is that it's now a 3.5-legged robot rather than a 4-legged robot. This simulation doesn't explain all 17 actions perfectly because 16 of those actions were performed with the physical robot, with the undamaged robot, but it explains more than any other simulations. As the robot collects more exploratory actions in its damaged state, this is going to become more and more accurate. This is the only simulation that's going to explain the 18th and the 19th and the 20th action, and so on. Logan, you have a question. Go ahead.
Yeah, with the 9 pieces, was it a requirement that the robot had to use all 9? Because I know it's no longer using one of those motor joints. So is that allowed for it when it's doing its own self-design to just kind of drop one and not use it anymore?
That's a good question. We didn't put that in. So the robot was kind of forced to use all 9 pieces. But as you can see in the simulation here, maybe you can see it in the simulation here, right at the end, the right lower leg is actually there. The evolutionary algorithm has just made it so small that in effect it shouldn't be there. So by making it small enough, in essence, it can sort of ignore or get rid of pieces.
Okay, thank you.
Yeah, it's a good question. So, what aspects of the simulation do we place under evolutionary control to allow it to explain the broadest range of experiences? So it's kind of like the minimal spanning set in algebra. What's the smallest alphabet that the robot can use to describe its situation? Okay, so the robot has now re-evolved a new simulation, a new understanding of self, but the mission hasn't changed. The mission is still, no matter what's happened to you, get from the left side of the table to the right side of the table. So we pause the first evolutionary algorithm that's evolving simulators, and we unpause the second evolutionary algorithm, which is evolving controllers on the evolved simulation. The evolved simulation is now changed. We have a 3.5-legged robot. So the way of moving the controller from before no longer works. It got high fitness on the simulated undamaged robot. But that same controller, when it's rerun on the simulated damaged robot, has a drop in fitness. So evolution has to evolve a new controller. And evolution in this case comes up with this particular controller, which causes the robot to move in a very different way than it did before. We talked about perverse instantiation several times in this class now, which is, and you've probably seen this in your own, with your own code base, is that often evolution will produce a solution that has high fitness, but it instantiates the desired behavior, or it instantiates the fitness function in a perverse way, not the way you wanted it to. You'll notice that although this robot does technically get from the left side of the screen to the right side of the screen, it does it by turning 180 degrees, so that the front of the robot is now pointing backwards and vice versa. Whether this is really a problem or not, who knows? This is kind of a toy mission, so maybe it doesn't matter that much. We take that evolved controller and we play it on the damaged robot, and we get this. You remember our discussion about legged locomotion. This is certainly not an energy efficient gait. But from the point of view of NASA, it's better that a mission continue even at 50% functionality or 10% functionality rather than complete mission failure. If a rover loses a leg or there's some serious damage, it's millions of taxpayer dollars, years or decades of effort at stake. Let the robot try and figure out what the problem is and find a way, if it can, to recover. Okay, so here's sort of here's the big picture of what we just saw. We have estimation over here. The robot is trying to estimate a simulation of itself. So in this cartoon, the robot is has a population of just 4 simulations. It doesn't know which of these 4 is correct. We know this one is correct and these 3 are wrong. We have a second evolutionary algorithm down here, which we call exploitation. The robot is going to exploit an accurate simulator once it has one. It's going to exploit it to evolve a controller to fulfill the mission, which is to move from the left side of the table to the right side of the table, and then we transfer those controllers to reality. There is a third evolutionary algorithm that is running, which we haven't talked about yet, because this one takes a little bit to wrap your mind around. And this comes back to Hannah's observation that the robot should not perform randomly. It should act in a way that breaks its current hypotheses. What does that mean? Let's assume at this point in time that the robot thinks it's either put together in this way, this way, this way, or this way. And the robot is trying to consider what to do next. So over here in exploration, these are 3 different evolutionary algorithms. Each has its own population. This one has a population of simulators. This one has a population of neural network controllers. This one has a set of actions, not neural controllers, but just actions. Which of the 8 motors should be rotated downward and which motors should be rotated upward? You can think of each genome in this population as a binary string of length 8. A 0 represents rotate the motor upward. A 1 represents rotate that motor downward. So there are 2 to the 8. There's 256 possible things the robot can do. Which thing should it do next? The fitness of each action is, as Hannah said, how well it breaks the current explanations. So imagine we have this population of actions. We take the first action and we actuate, or we use that action to actuate the first simulation. In this case, let's imagine that it causes this simulation to stand up, and there is no tilt information in the main body. The main body is flat. We take the second simulation, we provide that same action to it, and in this case it tilts left and a little bit forward. Take the same action and supply it to the third simulator. The main body tilts very far to the right. We take the same action, supply it to the fourth simulation, and it rotates a little bit to the left. So we've taken the first action in the population of actions, sent it to each of the simulations, and we get back 4 sets of vestibular repercussions. How did the robot respond to those 4 actions? The fitness of that action is what? How do you think we calculate the fitness? What is the quality of an action after we've sent it to each of the 4 simulations and got back 4 sets of vestibular repercussion? What is a good action in the exploration evolutionary algorithm? And what is a bad action? We want to evolve actions that break these simulations. What do we mean by break? How do we formalize that? Anybody have any ideas? This is the trickiest of the 3 evolutionary algorithms here. Alex says, the fitness could be alignment with predicted and observed motion. That's the fitness over here in estimation, right? When the simulated robot moves, we want to align, or we want the difference between simulated sensor data and physical data to be as low as possible. The lower the error, the better the simulation. That is not the case over here in exploration. What is the fitness of an action if we send that action to these 4 simulations? Remember that this action is not something that's been carried out on the physical robot yet. The physical robot is trying to use the exploration part of this system to determine what to do next. Out of the 256 possible actions, or as it's evolving actions, it's looking for just one action that it's going to run on its physical body in a moment. But it doesn't know which one to run. It wants to run an action that breaks these simulations. But how do we know that before? How do we assess that for an action before that action has been executed by the physical robot? This is tricky. There is a way to know. What is it? Logan says, wouldn't you want to reward the greatest difference in outcome between various simulations? That's exactly right. In this cartoon here, a single action has performed all 4 green cubes to tilt in different directions. The fitness of an action is the variance, or the amount of difference between these 4 sensory repercussions. If we go to the second action in the population and we actuate this sim, this sim, this sim, and this sim with that second action, and the amount of disagreement is less, the difference between the rotations of the 4 green cubes is less, then that action has broken the simulations less. We're looking for an action that causes these models or causes these simulations to disagree in their predictions. So I'm just going to type this into chat to emphasize. The fitness of an action is its ability to induce difference in predictions among the simulation's hypotheses. The fitness of an action is its ability to induce. It causes these simulations or these hypotheses to make different predictions. If we supply an action to the simulated robot, the vestibular data we get back from that simulated robot, it's a prediction. This simulation is saying, I think if you do this action, this is what's going to happen. This simulation says you're crazy. If the real robot performs that action, he or she is going to feel this. The third simulation says you're both nuts. If you perform this action, this is what's going to happen. And the fourth one says, I don't know what's wrong with the three of you. I know that if the physical robot performs this action, this is what will happen. They disagree. Okay. So this evolutionary algorithm is going to search the space of all possible actions. In this case, it's a relatively small space. There's only 256 possibilities. It's going to search this space for the action that induces maximal prediction difference. When it finds it, that action is then going to be performed on the physical robot. And by definition, whatever physical vestibular data we get back from the physical robot, that physical data is not going to match all of the predictions of the four simulations because the simulations disagreed. We know that because this simulation is correct, whatever action the exploration phase outputs and the physical robot performs, the error between this sensor data and this sensor data, the error between these two sets is going to be low, and the error is going to be high among the other three. Not all of the simulations can be right because they're all different and they all disagreed. So if we perform that new action and then we continue evolving in the estimation phase, the fitness of these three simulations is going to decrease because these three cannot explain the sensory repercussion of the new action that was just performed. Okay, this is a subtle point. It takes a little bit to wrap your mind around this. The reason I'm spending so much time on this is this became, after we published this paper, this work became of interest to developmental psychologists who study human infants and how human infants grow into adults. There's a very well-known phenomenon among children known as motor babbling. We all did this when we were kids. If you have any younger sisters or brothers or cousins or nephews or what have you, very young children, they're always moving, or most of the time they're always moving. They're shaking their arms and legs, they're looking around, they're twisting their heads, they're kicking their feet, they're grabbing anything in their environment, they're trying to put those objects in their mouth. They're always moving. They're not verbally babbling, they're babbling with their motors or babbling with their muscles. There is a common belief in developmental psychology that motor babbling is random, that the infant is just, the brain and spinal cord of the infant is just sending random electrical impulses to the muscles to see what happens. As we've shown in the Resilient Machines project here, if you actually go back and you look at this project and you only look at the physical actions, if you only look at the physical actions that the robot performs one after the other, as I mentioned, it performs 16 or more actions. Each of those actions, one after the other, look random. The robot is doing different things. There doesn't seem to be any rhyme or reason to what the robot is choosing to do. But we know that only the first action is random. The second and subsequent action are very carefully designed internally by the robot to break or disprove the robot's current understanding of itself. There's work now going on in developmental psychology to try and understand whether human motor babbling is doing the same thing. It's hard to actually perform these experiments or know. Is the child consciously or unconsciously thinking to itself, I think that if I reach out in this way, I'll feel this weight on my arm. Or actually, if I perform that action, maybe I'll feel this weight on my arm instead. Maybe internally there's a discussion going on and there's a disagreement about what will happen if a particular action is carried out. As adults, we're maybe not aware that we're doing this so much, but sometimes it feels as if we are. If you've ever grabbed a jug of milk out of the fridge, and if it's an opaque jug, so you can't see how much milk is in the jar, sometimes you're surprised if there's much more or much less milk in the jug than you expected, and you kind of jerk in a surprised manner. That's because you had an expectation about when you pulled on that jug with certain force, you had an expectation about the sensory repercussion, how much the jug was going to resist your pull. And if there's a disagreement among what you actually feel and what you're predicting would happen by that action of grabbing and pulling on the jug, your brain kind of wakes up and you're a little bit surprised and you suddenly pay more attention to the jug of milk than you might have otherwise. There are certain hints there are certain hints that come from day-to-day action that suggests our brains, even as adults, that we are doing this all the time. We are making predictions about what might happen in the real world, and sometimes we might be generating actions not to get a particular job done, but to learn something about the world. If you're holding a jug of milk and you're not quite sure how much milk is in the jug, there are certain actions you can perform to figure it out without having to look inside and see how much there is, which is to shake the jug back and forward. You can hold the jug and twist the jug about its long axis, and that will not tell you anything about how much milk is in the jar. It is not a good action from the exploration point of view. There are different actions that will tell you something about reality. Okay, just wanted to digress for a few minutes on this. As I mentioned before, one of the things I love about robots is not just the robots themselves, but they help us generate questions about ourselves, about how human behavior and human development, in this case, proceeds. Any questions about that before we push on? All good? Okay, so just to quickly review, this project is kind of involved. We have the estimation algorithm over here where the phenotype, or the thing that's being produced by the genotype, is a simulated body. Fitness for each of these simulated bodies is the similarity between the sensor values generated by that simulated body and the physical robot's sensor values. We have the exploitation algorithm over here where the phenotype, the thing that's produced by the evolutionary algorithm, is a neural network controller. And as always, the fitness here is simply forward displacement of the best simulated robot from up here. And I don't have a little bubble for the exploration one, but we just went through it. The phenotype here is a simple action, rotate a couple of the motors downward. And the fitness is disagreement among the simulations. Okay, I just walked you through 17 cycles of one run of the Resilient Machines project, which at the end of the 16 actions at least, with the undamaged robot, produced this simulation, which is shown by the thick colored bars. The outlines underneath the thick colored bars are meant to represent the actual way in which the robot is put together. And I've drawn these little black lines to show error. You can see that the evolved simulation in color here is not perfect. Some of the legs are bent. We went back to the beginning and did another 16 actions alternated with 16 runs of the estimation algorithm. And again, the robot comes up with a good description of its own body, but some of the legs are tilted. It's not perfect. We did it a third, fourth, fifth time. The sixth run, the robot actually didn't do very well at all. The seventh run didn't do very well at all as well. It had some of the parts in the wrong place. We did 30 trials in total, and you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of those 30 runs, the robot at least was able to figure out where all the pieces were supposed to go. So, not bad. Okay. Ultimately, this project is meant to address the sim to real problem, or the reality gap problem. It does a pretty good job. Here's the simulated or the evolved simulation from before. I've actually shown you this picture before. Here's a one-to-one comparison between the simulated behavior and the physical behavior. Most of the time it's very close, but there are a few points during the gate cycle in which the inaccuracies of the simulation show up as inaccuracies in behavior. Close, but not perfect. I think in the interest of time, I'm going to skip over this figure. You can go and read the paper, which is the reading for lecture 17 that goes into more detail about this plot. Any questions about the Resilient Machines project before we push on to transferability? Oh, all good? Okay, so we're going to look at a fourth attempt to cross the reality gap. We're moving in chronological time, late 90s, 2000. I carried out the Resilient Machines project as 2006. A transferability project was reported in the literature in 2010. And the transferability project starts by asking the following question. Could the transferability of a controller be added to a fitness function? So we're going to go back to evolving behaviors in simulation. And we're going to measure the fitness of each controller as how far it gets the simulated robot to move. But we'd also like to know how transferable that controller is. So there's a second question, which is obviously, how do we define transferability? Intuitively, we know that it means that that particular controller, whatever behavior it produced in simulation, it should produce pretty similar behavior when executed on the physical machine. Okay, before we define transferability, we're going to assume that we're now going to have two fitness objectives. We're going to have two for every controller. We're going to try and write down two numbers: the amount of displacement produced for the simulated robot, and the second number, which is how similar the behavior is when that controller is run on the simulated and the physical robot. So we're going to shelve for a moment an actual definition of transferability. Let's imagine we have that definition. In this particular project, the researchers evolved controllers to maximize both numbers using a particular kind of evolutionary algorithm known as a multi-objective optimizer, or a MOO algorithm. Very memorable acronym. Some of you may be tackling the AFPO algorithm in the final project, AFPO, which is Age Fitness Pareto Optimization. AFPO is a type of MOO. So let's talk about MOOs first to see how these work. If we have two fitness objectives, or we have more than two fitness objectives, we could just write them down as terms in the fitness function and multiply them together. We've seen that many times already in this course. When we talked about evolving passive dynamic walkers, we multiply D, distance traveled by the robot, times a penalty term that penalized for a particular form of silly walking. We multiplied it by another penalty term and another penalty term, and so on. Multiplying a bunch of fitness terms together has problems, which we'll talk about in a moment. A different way to do this is to not multiply those numbers together at all, but instead to take our population, which in this case is a population of controllers. We evaluate each of those controllers, and we get back not just one fitness value, but in this case we get two. And I haven't said how we get this second one yet. We'll come back to it, but let's just assume we can get it. If we have two numbers associated with each controller in the population, we can treat those two numbers as coordinates in a two-dimensional plane. If we do that, we can plot all of the controllers in the population in a 2D plane. And in this cartoon example, let's imagine that it looks like this. This particular controller out here has high behavior, good behavior, but low transferability, which means that the simulated robot moves very quickly, but if transferred to the physical robot moves very slowly. Out here in the opposite corner, we have a controller that causes the robot to move extremely slowly. Behavior is low. Assume that behavior here is equivalent to velocity or displacement. But it's very transferable. If we take that controller and transfer it to the physical robot also moves very slowly. In the limit, you can imagine there's a point out here which causes the simulated robot to hold absolutely still. It's not hard to imagine that if you take that controller and transfer it to the physical robot will not move at all, right? But we're looking actually for a point up here. We're looking for a point that has high height, causes the simulated robot to move quickly, and it transfers well to the simulated robot. So the Mu is going to try and push these points or evolve points that move up and to the right. Okay, how do we do that? Well, a Mu is just a type of evolutionary algorithm, and all evolutionary algorithms that have a population mean that some individuals in the population are going to have to die, and the survivors, we produce randomly modified copies of the survivors. Which points in this picture should be deleted and which ones should be retained? If you have an idea, go ahead and type it into chat. How do we decide which controllers in this cartoon population to delete? And how do we decide which ones to keep? Any ideas? The most central ones, okay, so we could focus on these because these are close to the center, and the center is a little bit closer, to up and to the right. Missy has a similar idea, which is points that are closest to y equals x. We keep, and the others we throw away. Okay, maybe that's a way to do it. Other ideas? The tricky thing about what Logan said, which is the most central one, and what Missy said is the points that are closest to y equals x, is how close or how central. We could define a threshold and say you have to be this close, or we're going to take the top 5 that are closest to the center, as Logan was mentioning, or closest to y equals x, as Missy was mentioning. But that's a little problematic because we have to come up with another number. This is known as in machine learning, this is known as a hyperparameter. It's a parameter that describes how our algorithm works. How many points should we keep? How many points should we throw away? If we introduce that number, how do we know whether we chose well? If we say we're going to keep the top 3 that are closest to y equals x, how do we know that that's a good choice? Maybe if we had kept the top 10 or the top 5, that would have produced a better algorithm. One of the nice things about Mu, as you're going to see in a moment, is that you do not need to create another hyperparameter. We are going to delete some individuals in this population without having to come up with this third number. We have 2 numbers already. These are parameters. These are the things we're actually trying to evolve down here, transferability and behavior. So we're going to do it in a parameter-free manner. The way we're going to do this is we're going to look for what are known as dominated solutions. Dominated solutions in this case are going to be bad. A solution, or a controller, is dominated if there is another solution or another controller in the population that is better at both objectives. So we're going to visit each point in turn. Let's start by visiting this point here. It's not hard to see that this point is actually dominated by this point out here. This particular controller is higher than this point, meaning this controller produces a faster moving simulated robot. This point is also to the right of this point, meaning that this controller is more transferable than this controller is. So this controller or this solution dominates this solution, and we're going to delete all dominated solutions. So this solution is gone. I'm going to hover my cursor over a couple more points, and I want you to just type into chat D or ND. So you're going to vote for whether you think the point that I'm currently hovering my cursor over is dominated, D, or if it's non-dominated. A non-dominated solution obviously is one in which there is no other point in the population that is better at both objectives. Okay, here we go. How about this point? Dominated or non-dominated? Go ahead and vote by typing into chat. Okay. Absolutely, right? This point is dominated. There are 1, 2, 3, 4 other points that dominate this solution. How about this one? Dominated, non-dominated. Dominated. This point, dominated, non-dominated. This point, dominated, non-dominated. Non-dominated, right? If we visit this point, there is no other point in the population that is above and to the right of this point. This point down here is more transferable than this point, but moves less quickly. This one produces a faster moving robot, but it is not as transferable. Okay, so we can continue to visit each point and label it as either dominated or non-dominated. And we then delete all of the dominated solutions. What that leaves is what's known as a non-dominated front, which you can see here. It is a front. It is a line that, or you can trace a line through all of the non-dominated points where that front is hopefully in the direction that you want to travel, which in this case is up and to the right. We want to maximize both objectives. Here's a formal definition of dominated and non-dominated. When I made this slide originally, there's actually an error in here. One of the points is mislabeled. Can you see which one it is? There's one point that was labeled as dominated that's non-dominated, or vice versa. I labeled it as non-dominated and it's actually dominated. Which point did I mislabel? I should have put numbers on these to make it easier for you to tag them in chat. Anybody see it? The second one from the right, exactly. This one I labeled as dominated, but it's actually non-dominated. Neither of these 2 points is above and to the right of this point. Okay, so moves are actually kind of nice because, again, we don't have to come up with this hyperparameter. We just delete dominated solutions. In this case, that led to 6 deaths and 6 survival. Okay, so we now have 6 empty slots in the population. How do we fill those empty slots? We do that by randomly choosing a non-dominated survivor and producing a randomly modified copy of it. So in this cartoon, let's imagine that we randomly chose this controller. We made a copy of it. We introduced a random mutation. We evaluated this particular controller. And in this cartoon example here, this controller actually is a little bit better in terms of behavior and a little bit better in terms of transferability than its parent. So the child dominates the parents in this case. And as you can see, in this second generation where we have one new child, the front is moving a little bit more up and to the right. So as I just mentioned, we have 6 empty slots. We just filled one of the 6 slots. We have 5 remaining empty slots. So again, we choose a random individual on the non-dominated front here. This is also known as the Pareto front, which I might just mention by accident. Pareto was an economist who actually developed this idea of what's now known as Pareto Optimality. If I just back up for a moment, these 6 solutions are Pareto optimal. None of them is better than the other one. This is a little confusing because we tend to think in a set of things that there is one thing that's optimal and everything else that's suboptimal. Pareto, who is an economist, said, we can't think that way. Often there are multiple good solutions that strike different trade-offs between things we care about. You can understand how this would come from would come from someone who thinks about economics. Okay, we're adapting it here for optimization. There's a fascinating history about Pareto and the economic history of Pareto optimality, which you can read at your leisure. Okay, so we filled one of the 6 empty slots. We do this again. We delete all the dominated solutions, and you can guess what happens. This front starts to move up and to the right. And we don't need to trade off behavior versus transferability. If we multiply behavior by transferability, evolution has a hard time striking a trade-off between these solutions. One of the nice things is that if we're careful, the front stays spread out. We have lots of different solutions along the front that strike different trade-offs between behavior and transferability. This is one of the reasons why we like to use evolutionary algorithms, is evolutionary algorithms give us back not just one solution, but they give us back a set of diverse and good solutions that we can then, or the robot can then choose from. All good? Okay. All right, here's a picture from the actual paper. Like the cartoon I just showed you, they have locomotion on the vertical axis here. So distance covered in simulated meters. I'm paraphrasing here. So we're trying to maximize along the vertical axis here. On the horizontal axis here, we were just thinking about trying to maximize transferability. Here, they've reversed, it's the same thing, but they're just going in the other direction. They're trying to minimize simulation to reality disparity. So minimum values are good here, maximum values are good here. I tend to like, when I'm dealing with a MOO, to make sure that I define all of my objectives so that either we're trying to maximize all of them, push up and to the right, or minimize all of them, push down and to the left. It always gets hard to think about maximizing one and minimizing the other one, but for our purposes, it doesn't matter too much here. Okay, so what do we see here? This is a snapshot partway through an evolutionary run of this experiment. Like in my cartoon, you can see the black dots are non-dominated controllers. They cause the simulated robot to move quickly, and they transfer well to reality. Open circles are dominated controllers, and the X's are solutions from the previous evolutionary generation, and you can see that they're further down and to the right than the new solutions. So they're actually kind of showing 2 snapshots before and after in this evolutionary algorithm that's pushing, in this case, up and to the left. Any questions about MOOs or Pareto optimality before we go back and tackle a definition of transferability? So far, so good? Okay. Okay, so you'll notice down here they mentioned approximated simulation to reality disparity. They're approximating it. For each of these points, and the next plot, they plot the exact disparity. Here, they actually haven't sent these controllers to reality yet. They're approximating or trying to predict disparity before they actually know R, before they've actually sent them to reality. They took each of these controllers, executed them on the physical robot, and this was the actual picture produced. This is exact disparity. So this is a strong hint about how they define transferability, which we'll come back to. So let's come back to our question. They're trying to define transferability. We're going to maximize behavior and transferability. This seems like a pretty deep catch-22, however, because in order to compute transferability for each controller, you'd have to evaluate every single controller on the real robot, in which case, why bother with simulation altogether? If you're going to evaluate every controller on the real robot, you don't need a simulator. Okay. So they're going to, as we're going to see in a moment, they're going to try and predict transferability for many controllers before they send those controllers to reality. How do they do this? Well, again, let's go back to my cartoon here, which hopefully simplifies things a little bit. Let's imagine we're in the very first generation. We haven't sent any controllers to reality yet. We take all of our controllers and we evaluate them on the simulated robot. We don't know transferability, so all of these points, all of these controllers, we're just going to place them on a vertical line. We don't have a horizontal coordinate for these points yet. We don't know how transferable they are, but we know their height. We know for each of these controllers how fast it caused the simulated robot to move. Which of these controllers would you send to reality? We're going to send one to start, and then we're going to come back to Moo and continue evolving controllers. Which controller would you send? Would you send the controller that barely causes the simulated robot to move? Would you send the controller that causes the simulated robot to move quickly? Would you send the controller that causes the robot to move at half speed? Which one makes sense to send? As Alex says, Alex is an optimist, so am I. Let's send the top controller. Let's send the one that caused the simulated robot to move quickly. Maybe we'll get lucky and cross the reality gap quickly, in which case we're done. Okay. Here's the one that causes their simulated robot to move quickly. This robot's a little bit different from what you've seen before. You'll notice actually this robot is a wegged robot. It's got legs, and on the bottom of the legs it has wheels. Although in this particular experiment they locked the wheels, so it's just a legged robot. I wish we could have got to this lecture earlier. Some people like to make wegged robots. If you're doing some of the mini projects, you can try and turn your quadruped into a four-legged robot. They took this controller and transferred it to the physical robot and got this. Okay. They failed to cross the reality gap. Maybe not so surprising. So we come back to Moo. We now have a horizontal coordinate for just this controller, which is low transferability. There was high disparity between what the robot did in simulation and what it did in reality. If I were to now ask you, what's the next controller? Among these controllers, we're not going to do any more Moo for a moment. Which of these controllers would you send next? What's the intuition here? Half speed. Okay. Logan, why would you want to send the one that's half speed? If you want to unmute yourself and offer an opinion, that would be great. What's the value of the half speed one?
I was just thinking because then it might be easier to kind of rank the rest of them with respect to the half-speed one. So you could kind of like estimate it based on that because it's kind of the middle of the track.
Yep, that's a great intuition, right? So we were maybe overly optimistic up here. We don't want to send something that barely moves in simulation because it's unlikely to move in reality. So let's go to sort of half speed here. It's a good intuition. We're going to ground this intuition a little bit more by sort of exposing an assumption here, which is the one that we sent when we were overly optimistic. We're going to assume that similar controllers that produce similar behavior, that produce similarly fast-moving robots, are going to have similar transferability. In this case, this one failed to cross the gap. So this one here is also likely or is also similarly going to fail to cross the gap. So let's go somewhere else. Let's go somewhere where transferability, where behavior is different, and therefore transferability might also be different. Okay, we're at 9:45, so I think we'll stop here for today. We'll carry on with the Transferability Project Thursday morning. You're working on deliverable 2. You have a quiz due tonight. I hope you're all well. Have a good rest of your day. See you on Thursday. Bye-bye, everyone.